Hello? Okay. Just give me a moment. There you go. That should work. Why is that showing up? Whoops. Among Us. Oh, hi. Hello. Yeah, so I was just testing. I was trying to get I was trying to get what's it called? The shot, like this thing, this thing, this thing. I had this last time when I was streaming. Like what I had to do since I'm on Arch and there's no when you install OBS Studio, I guess you don't get browser. Like you just don't get like the browser like ability at all. So like I had to like compile it from source. It took me ages. But now I get like now I get chat. So it's good. Now I get chat. Starting a bit. Minus. This needs to go. What else needs to go? What are we gonna do this stream? I have it online. This one. Oh yeah, I gotta talk about this. And then that needs to be changed, possibly. This is important. Oh yeah, I released this blog post. I guess this would be a good introduction to the project. Yeah. I actually gave this a readme. Previously this did not have a readme. This was the readme. This, like, that's like not what you want. You don't even know what the fuck this project's about. Uh, yeah. So now this has a readme. So this is nice. This like shows some stuff at least. Yeah. Is my audio okay? Yeah, it should be fine. Yeah, and this is like a bit of examples here. All right, I think I'll start. Okay. Hello everyone. Welcome back. What's good? Yeah, I'm good. I appreciate it. Yeah. Okay. So, yeah. So when's the last time I streamed? Let's see. So like, okay, calendar's broken. Okay. Okay. So I streamed. Yeah. So this is the second week. This is the second week of streams. So hopefully, they're not train wrecks. This one wasn't that good. This one was good. This one like stuff was actually done. Um, this thing was a bit of a troll. But like now, this is the second week, and I've got a blog post, and the readme's up. Hopefully I can get some real stuff done. Hopefully this is a good introduction. Um, if you're interested, like my plans for this project, you just give this a read. You just give this a read. Because this is like this thing is like a manifestation of probably all of the important like big acting topics in like compiler theory, like compiler development. Like this is what I want. Like this is what I want out of it, right? And I'm just surprised why we don't have this. So I guess this thing is to maybe like give a go at getting all of these. This is like my like yeah. This is like my best try attempt or something, you know. I'm not very good at lean. I'm not very good at all of this stuff. All of this stuff's new to me. All of this stuff's new to me. Um but yeah, hopefully like you guys can follow me along on this project at least. Anyway, yeah, so this blog post is here. So if you're interested, just check it out. And there's a readme and everything. So, yeah, so I'm gonna go over like what happened between this stream and last stream. This stream and last stream. So, there's a so here, right? Previously, I think if you scroll down here, previously this theorem used to have this back and forth rewrite here, this like a spaceship kind of rewrite operator. If you go back to here, right? Back to here. There used to be a second operator. So they used to have this. So we used previously there was def rewrite if and only if n takes in this. It's a proposition and it rewrites forward and rewrites backwards. Basically, it's just like x rewrites to y and y rewrites to x. Right under this. So this is how rewrite if and only if was defined, right? It was defined. You rewrite this way, you rewrite the other way. So this the reason why I define it this way is like this makes intuitive sense because rewrite forward, rewrite back. This is stronger than rewriting only one way because if you rewrite this way, UB becomes more defined. But if you have any amount of undefined behavior on this side, which isn't on the other side, you can't rewrite this way. Like, you just can't do this. So what I originally envisioned, like my intuition for this operation, right? This operation basically represents equivalence of not only the functions, but equivalence of definedness, right? Like this thing would have like equivalent UB, right? Equivalent UB, equivalent like definedness. But in my head, right, I was thinking that, okay, this rewrite thing, this is what I was thinking of. So we have this, right? Is this equivalent to x equals y? Is this equivalent? So this is propositional equality. This is like incredibly strong. Like if you have propositional equality, like literal like equality, like mathematical equality, if you have this, you can basically do a rewrite. You can just rewrite x, and then all of the x's become y's. Like this is as strong as can be, really. Like you can have, if you have this, y is a stand-in for x and x is a stand-in for y. Like they mean the same thing in different contexts. So I guess like the thing that I talk about is rewriting this way. This is not equality, right? Because if you have poison here, this rewrites to whatever you want, but whatever you want is not equal to poison. Yeah. So like I didn't think that if you can rewrite this way and you can rewrite that way, I didn't think that that means they're propositionally equal, because I was thinking in my head that maybe the undefined behavior on this side is not can like, let's say, like I was thinking like maybe you have like two cases, right? You have undefined behavior and that rewrites to y, right? But then you have a second case where undefined behavior, we have second cases where x, you have ub here, right? And then I was thinking like, okay, you can have this case, right? And this is obviously not equality. This is not equality, but apparently it is. Apparently, if you can rewrite this way and you can rewrite the other way, they're propositionally equal. Like apparently. So there is a proof of this, and this shocked me. But maybe I think my intuition's off. Oh my God. Yeah, maybe my intuition's off, really. So here's the proof. So if you can rewrite forward and you can rewrite back, this is an equivalent statement to just saying they're equal. And I mean, the proof is just like, it's just like case bashing. Like, so here, right, you basically want to prove an if and only if, so you need to use the constructor tactic. So basically, to prove that this thing is equal to that thing, you have to basically prove, so basically if you prove P if and only if Q, you need to show P implies Q and Q implies P. That's it. So what constructor does is it basically creates these two goals, right? So you start here. Constructor will bring it here, right? So you have two goals now. And then you can just access these two goals. So like, so dot and like, okay, I'm gonna prove this one. I gotta prove this one. So I gotta prove this implication. So I won't go into the proof too deeply, but really it's literally just case bashing. Like you just like here, take the cases, literally just like cool simp and everything. Yeah, so this is true. So this kind of freaked me out. So if you can rewrite forward and you can rewrite back, they're propositionally equal. So what the hell is the point of this operator, right? Wherever this operator is, you just write equals. And that's what I've done. So that's what I've done. So the rewrite if and only if. So which is basically equivalent to like that. The rewrite if and only if, that's gone. So I don't, it's gone now. So, so previously when we had this proof, right? This proof got changed. This proof has changed. Let me just show that. Yeah, so I use an equal sign. I use an equal sign here. Also, another thing that got changed, I previously, you might have seen, let's remove this, right? Previously, you might have seen cases X, cases X, case poison, simp Cases y, case poison, cases x, case poison. That's it, right? So previously you might have also seen this in the proof, right? Where we start here, and then we have x, y, and z. These are INNs. So these could be poison or not poison. So then we have like poison. These could be poison, 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 poison. But we don't want to work with poison, obviously. So we'll just take cases, right? Cases. X is poison. Well, if X is poison, um, all of the places where X's get replaced with poison. So you just have poison here, here, here. But poison poisons the entire expression, right? If you have UB, it'll just simplify down to poison equals poison, right? So you can just simp it away. So that goes away. And then, okay, so we have bitvec here. Okay, well, we need to get Y out as well. So take cases on Y, kill the poison, cases on X, kill the poison, and then we're left with bitvec, 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 bitvec here, right? So this is what the proof used to look like here. And I did like a simp all to turn these into actual nice inequalities. And then now you don't have to think about poison, you're only thinking about bit vectors now. So this is gone. I removed this because I remembered that I had a tactic that automatically did this for me. I just remembered that. So this is the tactic that does it for me. It's the exact same thing that I've written out. It binds the variables properly. So if I go here, right, this just turns into what I wanted. And the implementation of that tactic is a macro. So I wrote this months ago, but I just forgot. So how it works is it's basically more of the same. So it's like cases, bitvec. This is like a goal synthetic placeholder. It's basically like a stand-in for the goal. And then all of the poison cases get simped out. And then that star there means you just run it recursively on all of the inputs. And then at the very end, we just simp all the hypotheses. So these turn this hypothesis, which works on poison, into an actual nice one, which is inequality. So this is a really nice tactic. Yeah, I just forgot that I even had this, but so I have it now, and that makes my life easier. So, and the rest of the proof is the same. The rest of the proof is completely the same, except here, this thing, right? I have hx, hy, hz, hz. Instead, I move that to one hypothesis. The reason being is because I wanted to support positive and negative. So we prove the positive part, right? The positive part's right here. So I just put it into the main proof, which does positive and negative, because I just changed the proof a bit. Because I mean, it's basically the exact same, the positive and negative, right? Going back to here, this proof, right? Proving that if A and B don't overflow, but B and C overflow. So A and B don't overflow, B and C overflows. So what we want to prove is B plus C is greater than B. And then anything that's greater than B, obviously, like if A plus B overflows, A plus something bigger than B overflows. That's what we're trying to show. That's what we're trying to show. So for the positive and negative case, here's the positive case. Positive case is very similar, but the negative case, you can't really prove it in the same way we did this one, right? Because we did omega on both sides. If you do omega on both sides, you can't really prove it. The reason why I can't prove it is because this side's a contradiction. This side's a contradiction. So what this is trying to say is, when we get after here, right? What it's trying to say is, this is a contradiction because if you add A 2 int plus B C 2 int, like this is like less than something, but if we add them both together, it's greater than 1. Like this is a contradiction. Because like in the negative case, A plus B should be negative, right? A and B are negative. If you add two negative numbers, that's a negative number. But apparently, we can deduce that they're both positive, and they're actually greater than one. But that's a contradiction. So that clears the goal. That clears the goal. So yeah, so there are differences between the negative proof, but not much. Like this is the only thing. Um, it's mostly the same. Like it's basically the exact same. But yeah. So yeah. To access the positive and negative parts, you take cases. So this is positive if they're positive. This is negative if they're negative. If they're all negative. Yeah, it's the same. So yeah, I guess that's all of the preliminary stuff. Yeah, yeah. So we have some pretty good foundations here. Like it's pretty good. It's pretty good foundations. So where we should start is probably uh some like proof automation like this. This would be like a simple one. Okay, so uh the hold on, give me a moment. Give me No worries. Okay. So we need some. So we'll just do some proof automation stuff. So this is. I'll explain this for a second. So this will be a lot of this will be a big performance improvement. So let's see. The proof here, right? This is a very. See how long it takes to type check? It takes like a while. Like if I like just go back here, right? It just takes a while. Why it just takes a long time. I'm guessing the reason behind that is these simplifications. So this simplification, these simp in rules, how it works is, if you look at all these definitions here, basically simp in basically removes the definitions. It'll basically take, let's say you do this, right? It'll basically unfold the add no sign wrap definition and replace it with this. Um, it basically just simp in basically removes the outer layer. That's it. Just removes the outer layer. But then it runs the rest of simp. So what happens here is if you go into the definitions, right? It runs the rest of the simp stuff. So then it runs all of these, right? Because it can find p bind 2 in one of them, right? So it runs all of these. So it's like it splits all of these. So like p bind 2, if there's like an if, it puts them on two different sides. It does all of these simplification rules. It does a ton of stuff. It's like a really big piece of proof automation. Um, and this allows you to go from here, right? This allows you to go from here. If you have a poison here, it just gets rid of the poison, right? And then brings this to this. So it's a lot of steps. Actually, if we do simp only, it'll tell me what it uses. Well, not simp only. Simp that. So these are all the lemmas it uses. Which I mean, that's not that much. It's actually pretty normal. But yeah. So the goal is what I want to deal with. Maybe I can find a different case. Maybe I can find a case that doesn't take a while, right? Did these take a while? Yeah. So it's really let's see. Rewrite. I show an example of where I want to optimize. I show an example of where I want to optimize. So the simp in stuff used in this tactic, this proof, it is necessary to use all of those lemmas. It does take a while, but unfortunately, it does use a lot of those. But what I want to do is, let's say like if we take this. We take this. I want to see how big the proof term is. And so that's not what I wanted. Fuck, I hate Copilot. It's just bit back. Or I mean, I can just do this. Okay, and we can prove this easy. But the proof term is huge. Like I think it's huge, right? Yeah. Okay. The proof term is huge. This is my issue. So, like this is big. Like see, rewrite forward back implies equals this. Like this proof term. These I should really have a tactic that goes like, okay, if there's poison on one side, we know that this is just poison. These should be like automatically proved. Like this proof term should be like really small. So for example, like if it were to see this, like this should become a new simple lemma. So if it sees something like this, right? How big is the proof term here? It's just as big. Okay. Why isn't it? I should just use this one, right? Okay, how big is this proof term? Okay, so this proof term like unwraps. Why is it unwrapping? Why don't I just do like what is this? Isn't it more like just like exact, right? Yeah. So if I do this, so like it's an actual lemma, and then simp. How big are these? Why are these different? Yeah. See, like what I want to do is I want to remove like this big proof term. Like for example, like here, right? If I have poison plus no sign wrap, this should just be immediately rewritten to poison, but it takes a while to go through all of the lemmas to unwrap the poison. So it's not visible here. Like obviously these two proof terms are like just as big. But I believe that there is like some slowness like happening. Like when like because this takes a long time to run. This takes a long time to run. So I think I need to add things to unwrap, like when you get to poison here, like unwrap this, and yeah, to unwrap this, and then add like some maybe like domain like specific rewrites as well. But yeah, so that's basically what I want to do. And I'll show you another place where this would be very useful, because I do have like something like this. Let's just unwrap. Let's unwrap. Why? So how about let's do this, right? Okay, to prove this, this is like a really like simple like lemma. I just do like sim. I'll just try and like bash it. So this is commutative? Maybe I have this proof somewhere. Do I not have this proof? How about this, right? And then set overflow. Okay, and then just rewrite as sad overflow com. What's left? False implies this intro. No overflow. Oh yeah, this is just unnecessary. Okay, so just intro this. Add. Yep. Okay. So there's another tactic that I have that can use these. So this is a quality. This is just like straight up a quality. But the reason why I do this is because I want to show you this tactic that I have. This existing tactic that I have. So if I have like x no sun wrap y plus 20, we wrap to this plus 20. Okay, so how do you really prove this? If you don't really want it, you want to actually like do a rewrite like a compiler does a rewrite, right? I mean, you're proving all this stuff, but you can't actually do a rewrite. So like, this is what we have to do this rewrite. So this is a tactic that I wrote a while ago. I need to redo it. Basically, I need to like rewrite it at some point. It's basically you see here, this is a rewrite. It's not a quality, so you cannot use the inbuilt rewrite tactic. Rewrite has no idea what this relation does. There's no idea. So I had to write my own one. So if you see here, after a rewrite, forms the rewrite, and like, okay, what's that? That's just RFL. Yeah. So this is what RW is calling. So it's basically the RW tactic for rewrites. So that works. That works to solve it. But under the hood, this proof term's huge. Like under the hood, if we look at how this tactic works, basically how this tactic works is that it uses this Conger app. This is the entire thing behind rewrites. This is the entire thing behind rewrites. What it does is think of this function f as an expression in terms of a, right? So it's basically saying if you take in this hypothesis that says a rewrites to a dash, then expressions in terms of a rewrite to expressions in terms of a dash. This is called congruence, like rewrite congruence. And this is how, because like equality has congruence. Eq.conger, or just like congruence. So equality has congruence. But since equality works both ways, it's like really strong. But rewrite has congruence. So this is a thing that you can do. But it has to be proved. So I did prove it. But the thing is in here, right? The only way to apply this theorem is if you have this kind of like well-formedness, like predicate thing. This is basically saying if you put poison in an expression in terms of A, you get poison out, right? Poison has to pass through. I think this assumption is a bit too strong, but that's like for another day. But this works just fine. So this how rewrite works is it tries to basically construct an expression in terms of this and uses this to rewrite. So an expression in terms of A rewrites to an expression in terms of A dash if you know this, right? And then that A rewrites to A dash is this thing, right? So an expression in terms of this A dash rewrites to an expression in an expression in terms of this, which is A, rewrites to an expression in terms of this, which is A dash. Yeah, that's so it relies on this Conger app. But to actually get this well-formedness like predicate thing, like if you put in an F, a poison comes in, then you get a poison out. To get this, right, this is it's like annoying to prove. And the way I prove it is just by doing simp.in. So that's why the proof terms end up huge. If I go here, right, we want to, there's congruent proof, right? Okay, so here, right, I'm trying to apply Conger app, right? Conga app is this thing, right? So for me to apply it, I need the motive, which is this function, and I need the proof that the motive actually respects poison. So to do this, I prove congruence in here, and yeah, see, I got a to do in here as well. So this is this basically does simp. This basically runs yeah, it gets simp theorem. So this basically runs simp in, and this takes a while, and the proof times get huge. So I want to make a custom tactic. I want to make a custom tactic called poison propagate. All it does is propagate poison. All it does is propagate poison. So I guess we can just start by doing that. So it won't be like too much of a custom tactic. It'll basically just be a macro that calls simp with a simp set. So here, whoa, this is how it will work. This is how it will work. So in here, look at like tactics, right? I think I'll just do this thing. In. Well, I think we'll add it here. We're gonna add it here. So this is where all the tactics are. Okay, so we should let's. What are we gonna name it? We'll just name it like, I think just the name I have here. So poison propagate. This is just a tactic, and what we'll do is basically this will just simp. It'll just simp with it'll just simp with this simp set. It'll just simp with this. So we're gonna actually define these set of simp lemmas. So I have them here. I'll just copy this. That's it. And in here, I'm just gonna get Copilot to just do all this shit for me, because I don't want to do it myself. Yeah, it's just like so this could be done. This could be done with like a custom tactic. But I mean, if I can just like copy paste this shit a billion times, I mean that's just fine. That's fine by me. So this is poison. Poison equals poison. So this is like poison. So we'll start like this, right? So add poison equals poison, just basically inn. This returns this is basically a lemma that's just saying x plus, let's unwrap, poison equals just poison, and the proof is just by no. How do you prove this? No, that's just a simple proof. This is one unknown attribute. There you go. Okay, and then just spam it. Come on, keep going. That's not right. Okay, so we'll just start have this, right? Poison. This is the only thing this shit is good for. Yeah. Add no wrap. Poison equals poison. Yeah. Okay. And then we'll just see how that works. So when I do this, what I could do is, so let's just like get out. Let's just get out what this tactic is doing is just this. It's just exact. And this is basically a function. X plus 20. What am I missing? Well, formness is literally just by simp in. What else is missing? And then this, right? Oh. There you go. So this is basically what this tactic is doing. So let's see. And then we'll use the different one. Yeah, so this doesn't run. But what if we just do this, right? Poison plus 20. What is plus? Surely plus is like I handle plus, right? Oh shit, I don't. Okay, well obviously because I didn't fucking do this. Whoops. There you go. There you go. Okay, now is this smaller? Is this a smaller proof time? Probably not. But I mean, I guess because it this thing, right? This is basically saying that this is equal to poison. This is so huge, but it only should use a couple things. Maybe because it's inlining these. What if I make these like irreducible? Is not a definition. Well, I mean, of course. Yeah. Maybe because these are name-spaced? Because, for example, like rewrite. This one's like name-spaced. I don't know. Maybe like, I want to see what happens if I put this in the namespace. What if it's like, is this like simp only? Oh, okay. So it is small now. Okay, if I do simp, I think it's just like because it is simp only. What if I remove this? Because I believe it runs thing in reverse order. Yeah. Okay. So it runs things in reverse order. So it's running all of the well, not in reverse order, the actual order. So it's running all of the like huge stuff, and it doesn't get to these things. Doesn't get to these. Um. Yeah. Okay. And then that's tiny. That's what's it called? That's a tiny proof term. So how do I guess maybe I can maybe I don't need this. Maybe like I don't need this. Maybe I can make this simp in, but change the, because for example, like I can like change the priority. I can change the priority. So then if I change the priority of these, when I do simp, these should just go first. Yeah. Okay. So changing the priority works as well. It works as well. Okay. Okay. Well, I can just make this, right? I can add that, the default parameter. Oh, unknown tactic. I guess it's because it's like a dependency cycle. I mean, that's fine. Yeah. So this is yeah, okay. So I guess adding a priority makes it better. So this kind of proof automation, this needs to be this needs to be a lot bigger. Like what's it called? Yeah, I need to add proof automation for changing the commutativity and like associativity of stuff. So for example, like if I have like x plus y plus z, if I have this, right? It should really like go to a normal form, which is just like x plus y, y plus z. Like all so like when you're thinking about like addition like this, it should never show up like this. Like it should just be simplified. So that's something I want to do as well. So yeah, I think this can be moved later on when we prove more theorems, but proof automation like this, yeah, so ACNF is rewrite aware as well. Okay, so I'm gonna do a test. So we know this is like an example of a theorem that isn't inequality anymore. So this is like an example. So we have this. Plus y. So this is a like interesting one. This uses undefined. This uses the properties of undefined behavior. So so to prove this, we know that this is true because we're just defining the behavior where it wasn't defined previously. We're just defining the behavior. So we can just say we'll do this like by cases. By cases, a plus set overflow b. So in this case, so we have two cases. So in this case, it's true. So you can just rewrite. I think it's like this. Overflow Bivec, and that's poison, right? Why is that a problem? Oh, H. Okay, so now this is poison, obviously, and then we can literally just exact. Oh, is this like trivial? Sim? Yeah, or just like literally like just this is like better. Is it like exact? Yeah, exact poison rewrite. Obviously, because poison rewrites to anything like that. Okay, and then if this isn't true, rewrite s at, yeah, neg or not. Yep, and then this is there like a way to simp this thing? Is it like desimp something? Unfold. Because this is hey chat, right? Or something. What the fuck? Why is simp going the other way? It's like turning this. I guess like that's like inequality. Oh yeah, okay, so that's working. And then simp iron or something. There you go. So all right. So this is something we proved. So what this is basically saying is um these functions do these operations do the exact same thing. Like they do the exact same thing. It's just that this has more UB than this. This is more defined than this. This is less defined. So this is what this is like if we wanted to have associativity, for example, right? To get associativity for no sign wrap, you need all of these conditions, right? But what LLVM does is, if it sees something like this, so when LLVM sees something like this and they want to do reassociation, what it does is literally what I believe it does is, I think it just converts all of these to this. It converts all of these to this, and then does the reassociation. Then that's okay, like UB wise. Maybe it leaves. Does it leave like? I believe like you can't put any here. Maybe you can do that. Is that valid? No. Okay. So this is what it does. It just converts all of them to that. So there's like a weaker theorem. So add sock add. Yeah, so it just converts these, right? So it's just equivalent to this. It's equivalent to this. So this is simple, but it's no longer inequality because we're using rewrites now. So I guess it's just like applying this. So rewrite, rewrite, and then I think it's just like repeat. Yeah, I mean that's easy. And then just add a sock, right? I think hadd is like the most annoying thing in the world. Just give me a moment. I'm just gonna change the definitions. Yeah. Add. Okay. This needs to go. That's gonna be much better. Yeah. Okay, and then this is, I guess we need a theorem. We should need add a sock. How do these associate? Okay, it associates like this. Okay, and then this is, yeah, this is like simple. There you go. Okay, and then this is just, rewrite. Okay, so if you want to reassociate this, if you want to reassociate no sign wrap, the only way to do that is converting them. Just literally like just converting them. You have to use this. So add a sign wrap. You would go like rewrite, but it'll be like close to refine. Add. Yeah, should I call it rewrite or like rewrite? Refine. Because this like refines our undefined behavior. This removes the undefined behavior. So we can make this more defined. Okay, what's the problem? Oh, it's called test. Yeah. Okay, so when we call, we basically want to create a tactic called canon. What this basically does is it takes a huge, like a bunch of expressions, right? But what we want to do is we want to replicate this langref. We want to replicate their inst combine. What's it called? Reassociate. Oh wait, no, I'm in the wrong place. Not langref. Passes. Passes. Okay. And then there you go. That's what we want. So what reassociate does is, for example, if you see here, right? 4 plus x plus 5, these are in here, right? Obviously you want to get you want to turn these into constants, right? You want to move all the constants to one side, move all the indeterminates to the other side, and then all the constants on the right, these will just simplify arithmetically. So that's what we want. That's what we want to do. So I guess like example. This will take like the brunt of the stream. This will take a while. I guess we'll just do this example. Rewrites to what's this? We'll just make this like feedback. All right. An ambiguous term. I mean, fair enough. We'll make these like actual numeral literals better, like later. It's like 9. Okay, and then we'll just turn these into no sign wraps. So the goal is to transform this into something that's nicer. Obviously, like, I'm pretty sure you can just do that. All right. Can you just do this? And then these go first, right? And then you want to like swap these, right? Add com. Do we not have add com? I can just add that. Yeah, this thing's lacking. That's fine. Yeah. Why did I add Z? Yeah. So, and then you just want to rewrite with that. Shit, how do we enter in here? What? Oh. Okay. And then you want to okay, and then just like simp. Oh. Okay, yeah. Well, yeah, we gotta add like a simproct to move these. But basically, like this set of transformations is what we want, right? How can we automate this? That's the goal. That's the goal. Automating it. So I'm gonna get some water. And then I can show off the existing infrastructure I have for doing this, right? I have like this tactic, which is it's a huge tactic. What it does is literally performs optimizations. There was an example of it, but I deleted basically most of the code because it's just old. But I think we can. I think I can call it still. No rewrites were performed. Is there a way for me to call this with? Because I need to be able to mark something as a rewrite. Just like opt, right? How do I mark? This should work, right? No rewrites were performed. It's just like ideal. Okay. So okay, marking things. So this is basically a tactic. This ops here, it's basically opt to rewrite, but anything marked with opt ideal will get used as a rewriter. So this will just like apply it. So then we end up here. So the goal is to just apply these rewrites in like a useful way, right? Because if you get to here, it'll just keep applying it. It'll never actually like work. It'll never actually work. So yeah, we got to basically implement. I think do I have like an opt proc implementation? But yeah. So okay, I want to be able to define a function that allows me to do this like reassociation. It's like a special kind of rewrite rule. But yeah, so I'm gonna go to the bathroom. Get some water. I'll be back. All right, just give me a moment. Yeah, I'll be back. All right, I'm back. So I'm gonna rewrite. I'm gonna have to rewrite custom tactic. This stuff, this needs to go. Basically, I think I explained how it works. It literally anything tagged with opt ideal, it just applies them. It just applies them like over and over and over again. So, this is what I need to do. Yeah. Yeah. Okay. So I think I have an idea. My idea is to integrate this with simp, the simp infrastructure. So when I call simp on this, it'll run whatever simps, but at the very end, I'd like to, I guess like at some configured part, I'd like to run rewrites. But the thing is simp has no idea what a rewrite is. And in fact, like if you pass like this, like it would never know how to use it. It just doesn't use it. The reason why it's not erroring is because this is just like taking this as like a true statement. This is basically saying like this thing is true. So if this shows up in the goal, it'll prove it to be true, but it doesn't show up in the goal. Like this needs like this shows up in the goal, but this entire thing doesn't show up. We need to rewrite this. So I guess the way we can do this with simp is using something called a simproc lean. Simproc. Isn't there like a lean? Yeah, for the simprocs for the. This is like a blog. Okay. Could we do it like this? I think it might be better to rewrite instead of using the simp infrastructure, which simp is good, but it won't give me any control at all. It won't give me like any control. Like, yeah. Where is opt I? Okay, opt implementation. Okay, yeah. I think it's better if I just re-implement this. Yeah. 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 Okay. So my idea is at the moment, instead of using the lean expressions, it might be better to convert. Might be better to convert this. Let me think. Nah. No. Yeah, this is fine. This is fine. Okay, so first, the proof automation needs to actually check that these don't use any illegal things. So, for example, like you in here, you could put like an if statement, which is like if something stupid, then this, else that. Like, obviously, this needs to be replaced with these only need to contain like this is like has to be like a well-formed thing. So I guess we'll use metaprogramming. So we'll do it like this. So we will do this. Lab tactic test. This is a tactic. Hopefully I remember how to write tactics. So what we need to do is we need to import everything. and then run this. Okay, so the goal is what we care about. So the goal is obviously anything that we want to use. So we can get main target. So what is that? Expected type? Get main goal. Yeah. So this doesn't do anything. This will just run through the goal and check that it's something valid. So I guess we need like a list of valid instructions. Right? Yeah, we need a list of valid instructions. So I guess like the only thing in simpin are definitions, except for this. These are definitionally true. Does this break anything? This is just simp. Let me check if changing these break anything. I don't think these should break anything. No, they don't. Yeah, okay. So how I see it is anything with a simp in on it should really be only a definition and a definition only. So all the definitions under this should be valid. So I guess I'll just change these. I'll change these. I'll change this. Yeah, I want to change the name. I want to change the name of this so simpin only refers to definitions. So I guess like here, right? Simp simp def, so like in definitions. Or just like against definitions. Oh, whoops. Let's make this better. What? Unknown attribute. You kidding? Oh, these. Okay. Okay, this should be better. What? What? Do I not save the file? Oh. Um. Yeah. Yeah. Okay. So how it should work is any definition in this simp set, should any definition in that simp set should actually be an instruction definition. So to check if this function is well formed, it basically just suffices to check if the only definitions that are used in this thing are actually the simp set. So if we go here, I'm gonna change this to like inst definitions, right? And then when we actually check here, so if I, so to check if this is like a well-formed thing, so just like def e extra, so form. Oh, come on. Oh. Okay. Yeah, I really need to delete all this stuff in opt. Okay, so tactic well formed. Basically what? It's just a boolean, and this can literally be this can literally be something. So this is just like a functional thing. So I guess like match expr e with what is it, like in add this. Yeah, so a. So this is n xy. Sorry, it's false. So where do I use match expr? Do I use it anywhere? Match expr is basically like a thing that you get in metaprogramming. It'll just like match the expression, and then let you know. This is an inst definition. Okay, so I want to. How do I create the thing? Okay, so this I want to take in valid instructions. So is there a way to just like inst definitions dot get theorems? I don't think this will work. Because these turn into simp theorems. These aren't definitions. Okay, these aren't definitions. I have to write my own. I have to write my own thing. I have to write my own attribute that can actually mark these instructions. Because the point is I want a list of instructions that are actually valid. Because you can't just use any function. Okay. Yeah, so I want to change like all of this shit. Can I improve congruence goal? Yeah. Discard everything that just got changed. Just discard. 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 When I discard, I want to actually keep these. Ooh. I hate instances. I don't know why, like, when I try to use notation, it forwards it to these instances, and then I can't actually access the backing thing. I can't access the backing function. So I just define it over the top of it. Does that work? What else? Okay. That's discard. Yeah, you want to take all of these, make this simp in. I'm just undoing the crap. come on. What is it? Oh, that's not real. Oh, okay, well, it was something. Yeah, I think I might also remove this as well. Simp only, removing this is right, but keeping these, that's what you're supposed to do. And then when it comes time to do this, yeah, okay. Okay, good, back to normal. And so I just need to implement an attribute. Which is a pain in the ass. Okay. So I don't know how to do this, but I think I have code that is similar. How are attributes implemented? Just attribute? Oh, I have like a bunch of Zig code in here. There you go, okay. Maybe I can look into an old version of the code base which contains this stuff. Which contains it contains like a previous implementation of an attribute that I can just like take. Oh yeah, okay. How do I just like view it? Yeah, valid instructions. Yeah, I had an implementation of this previously. Okay. Yeah. All right, I'll just paste this entire thing. So what does this do? Valid instructions, tags. Definitions, inst. And this is just a hash map, right? Get entries. This returns a list. Okay. Yeah, so all I need to do is I just need to tag all of these definitions. So if I go to this thing, anything that has this, oh no, this shouldn't go any further. This should get inst as well. What's the problem with that? Expected string literal? Oh, these don't need a name, do they? No, they don't need a name. This is the name. Oh, wait, but it shouldn't be added. Okay. Okay, it should only be, inst should only be added on these. And we shouldn't take in a string literal. Yeah, string literal. Is there a way to use the definition name? Need syntax. We need syntaxing. It's just a name, right? A name to string. I'm going to just do like a list. List of names. And this just takes in names. M is a list. Oh, append. I was just like, how do I push? There you go. Yeah, okay, that's how it works. And then this doesn't need anything, right? This thing just works. Okay, great. So now I can put the inst attribute on the useful things. So okay, I'll just put it. I'm gonna put it on some of these. It's gonna take a while. Only some of these are valid instructions. It's gonna take a while. Great. All right. Why is this a problem? Not a definitional equality. Really? Why? What's the problem? Oh. Okay. That could have been a problem. All right. Yeah, so now all of the actual instructions get the instruction name. So inst, what is it named? Start. No. What is this named? Inst. So valid instructions. Valid instructions. I can just get entries, right? This takes in the environment, so get environment, is that? Oh, okay. So this is the instruction. So it probably like is good to turn this into a hash map. Right? Gaming chair. It's the same gaming chair. Look, it's the same one. Same one. Send me this file. Send me this file. It's good to see you. See you. How have you been? Reduce. Good. Yeah, I've been good. I've been good. Hi Lucas. Hi Kirby. Good to see you both. I've just been like just uni, but now I can work on some personal projects. Let me turn this into map. So I want to turn this into a. I want to turn this into a hash map, but I don't know how to do it. maybe Google. Basically, what I want is hash map. Hash map from A to B. What am I working on exactly? So, take a look at this, right? This is a blog post that I did. So the goal is to formally verify peephole optimizations in Lean. So basically, compilers are a program that turns your code into machine code, right? So the CPU can execute. And along the road of transforming the code, it makes it quicker by doing these things called optimizations. And optimizations basically change slow code into faster code. Basically, the whole point of this project is to create a framework to like prove that when you convert the slow code to the faster code, is it a correct thing to do? This is the entirety of that project. Like, is it the correct thing to do? So I've only had like 3 streams so far, but yeah. So it's basically turn this into a list. List like this. Is there a set? Oh, there's a hash set. Does this exist? Hash set. Basically, I wanna look. Does this exist? That's what I want to find out because that's gonna be useful for me. Perfect. It's off list. That's good. I love Lugal. Instructions dot stood dot hash set dot of list. This is the valid set. Hash set name. Well, let me just print these for a sec. Log info. Okay, and this just does nothing, right? Okay. Valid instructions empty. That's not good. Why is it doing that? Why is this empty? Okay. And sub. So I mean, I guess it is registering these, but it's empty. That's annoying. Thanks. Yeah. I reported him for terrorism. Okay. All right. Get entries. I don't know what the issue was. Well, I mean, what it is. Hmm. because it's package type and not mode application. Debug price. Okay. Registering a okay, it's it's registering it. In fact, it's actually making the list longer. Okay. So what's wrong with it? Maybe it's running in the wrong place. Might be running in the wrong place. I don't know the difference between persistent env and like these other environments. I might be doing it wrong. Am I doing it wrong? This is like the value. That's a state. And maybe this is like that's Olean. Okay, well I don't want that. Okay, what? Okay, get state works. What is get? What did I say? Get entries? Get entries gives me nothing. Get state gives me the right thing. What the fuck's the difference? In the current file? In the current state. Alright, fair enough. To hash set. String. Select a string. You really can't convert hash set to string? Okay. Yeah, okay. That's good. Alright, it works. Alright, and to check if these instructions are valid, it basically just splashes the check like match E with how do I check how do I check if this is an application? So if E dot is app of, oh perfect. Okay, so just I guess like it's just checking like is, yeah, is app. Is app of basically what I want to be calling in a loop, but that's slow. So like what is get app fn. Okay, so I just like copy this, right? So it's just like is app. If is not app, then do something, it else. So we want to match on otherwise return the input expression. That's so annoying. Why can't you just like match? I mean, yeah, fair enough. C dot and then we're gonna check if this is in the hash set. All right. What's this? Oh. Okay. Contains C and that's good, right? Too. Get app args. Oh, good. Okay. Perfect. Failed to show termination. This is not supposed to terminate. Well, I mean, it doesn't matter. Friends Trev, the given expression is an application. Oh yeah, and then we just want to check we want to check is it a literal. And check if it's a literal. So then we just like match expression. I guess not this, right? If so just like map explorer E with just like feedback. So yeah, so it could either be like in a well-formed like expression that like we give a shit about is it's either a natural number, not literal, yeah, feedback, poison, and then these are the only things that we care about. So yeah, these are the only things that we care about. So this takes in n bitvec. Yeah, so true. And then else, this is a e dot is nat is raw nat literal. How do I do it? Yeah, checking if like things are nat number literals. It's incredibly annoying. It's like the most annoying. Like I hate the metaprogramming. Like the lean metaprogramming is like really expressive. It's nice. I just have no idea what I'm doing. Nat, like it's shared code. Nat. Where did I have like alt proc? I think it's here. Yeah, this was the last one that I did ages ago. Oh, it's this one. Yeah, so I need to get of nat value. So if this is sum, this is just like true. Does get of nat value exist anywhere? Oh, in a do expression. Okay. This is E. Okay, and then this thing is just like checking. Is this an IN literal? And true. And then the rest, really. Bool M. Yep. Meta M bool. Oh yeah, here. What's the problem with this? All right. That could be fine. Okay. And then it'll just be walking. So then we'll just we just do this. Valid names. And then the expression. So it's just like M var ID. This is the goal. I don't remember how to get the type. The expected type. That's what we need. Yeah, that's how we get this E. And it's just like if this messes up, then we want to throw. So if this isn't, if this is like not, and we just want to throw. Throw. Throw exception, throw unsupported syntax, ill form syntax, what's the thing? Does it matter? Okay. Unexpected syntax. Tactic test. Okay. So where is it? Where is it invalid? What's the invalid one? Is it like? Maybe I can just throw an exception where the error happens. So it's just like here, right? So it's a valid expression. So this doesn't return a ball. This is unit. Okay, what's the problem? So if, and then what's this one? P unit? Oh, we want this. This types is like so annoying to read. All M, not all. I want to do just like, how do you just like run map M for all M. Reduce. I don't know much about functional programming. How the fuck do I? It's called like reduce or something, like L wrap, like what is it like? Surely, what's it called? Fuck, what's it called? What's it called? What's it called? It's like the thing in Haskell. It's not like reduce, like reduce. Fold. It's fold. It's fold, right? Okay. How do I just fold but like ignore the input? For in. Oh, whatever. Functional programming's failed me. Yeah. Okay, so the entire thing's invalid. Well, of course not, because we need rewrite. It's rewrite. Okay, so if with this is a rewrite. It's just like this to this. So it just takes in LHS makefs. You just run these both, right? And this one is equal. How does equal? How's equal defined? Two things in a prop, just like LHS, RHS. This is just that. Okay, that's fine, right? What's the problem with this? N. Where's N? Surely it's like here. N, that. E is just this entire thing, right? N. N. What? Surely it's like one of these, right? Why is that not printing? Oh no, it is printing. So checking that and that. So that's fine. There's nothing wrong with that. Oh, I know what the problem is. It's supposed to skip the first argument. It's supposed to skip the first one. I think it's skipping it, right? Is that how it works? Yeah, it's supposed to skip the first argument. Does that work? Checking X. Okay, well X is just an indeterminate, right? What would that be? Bound var? No, it would be f var, free variable. If this is a free variable. Okay, that wasn't so bad. That was a pain in the ass. That works. So it does check. It does check it. I'll probably delete this code later, but this is just a good reference in the meantime. So the point is I see the rewrite all of this. Most of these need to go. Hmm. What might be better is creating an actual framework around these things. No. Yeah, okay. Let's see. I think okay. Let's plan what we're gonna do next stream. And then I'll do one of these, right? I'll do this ACNF stuff, and then I'll close off the stream. Because I think what I want to do between this stream and now is like off camera is to basically redo a lot of this stuff to end up with like a really nice like optimization framework. Like all you have to do is just like write a function that just transforms an AST to a different AST. The thing is that I don't want to work on this AST, these expert expressions, right? I don't want to work on these because these are like these are the most annoying pieces of crap ever. Like these lean expressions, these are so annoying. Um, like they just are. Like working with these suck. So it'll be better to convert the lean expression into a custom AST, right? Like you could just do this, right? You can do inductive and expert, right? This is what I want to do in the past, right? I have an inductive, so it's just basically just like add add no sign wrap, and then like so on, and then this will be like the actual like AST behind the optimizer, like which will basically canonicalize the instructions, right? I want to implement this thing, so it'll just like canonicalize the instructions by applying these lemmas. So like this needs to be done. So I'll just do this off camera because I really don't want to do this on stream because it's just like a lot of work that really when I do something on stream, it should really be like entertainment. So like me proving stuff instead of doing like the foundational stuff. So the foundational stuff we move separate. So let me just like write that, right? So I guess like well, not here, but I guess like implement replace that and stuff behind opt. So they can be proved because you're in this framework as functions. You can just pass to opt. Then you'll be able to prove and so on. Is just to be a yeah, so like yeah, just a low level wrapper. Eventually you might want to prove these correct. Should be amenable to what's it called? Oops. Yeah. So what I'll do at the moment is I'll try and get an ACNF instance working. I'll explain what that is for a second. So ACNF is basically a tactic that canonicalizes things up to associativity and commutativity. I know that's a lot initially to explain, but really this is how it works. This is how it works. So this, for example, if you have x plus c, okay, we'll just, yeah. So if you have a goal like this, oh, I fucking hate Copilot so much. So if you have a goal like this, right? Obviously, this expression is equal to this expression. This is just associativity, but this is a thing that, like, mathematicians, they give no thought to this. This is something that, like, they don't think about. In their head, they canonicalize things up to associativity and commutativity, right? In their head, they don't see this side. They only see this side, right? So what mathematicians do in their head is really like uh, running this, right? So they basically automatically moves the brackets around into something, into a normal consistent form. So like, to solve this goal, it's really just like move the move the right hand side around. So this is what this tactic does. And this tactic is extensible. So if you go here, right? If you go associative, kappa. All right, so yeah, so I think it's called stood associative. If you, this is a type class, right? If you implement this type class, ACNF will be able to use it to reorder some things. So yeah, so this exists for nat. This exists for nat.add. It's just implemented. I think it's like yeah, I think it exists. So I just need to implement this for IN. What's EFN? What's that? Stop. Stop. Okay, so I need to import. I need to import I need to import this stuff. And okay, so I proof some. Yeah, so I'll move this here because I already have proofs for associativity and commutativity. So here, I already have proofs for this. So yeah, so it's basically just like instance for all n, really, instance for all n, stood associative in.add, right? This is associative. Don't know how to synthesize implicit argument A. Oh, of course. Yeah. So this is associative. What's the proof of this? Right? Why is it type mismatch? Okay. Yeah, so that's that works. And then we'll add commutative for that. Great. Now this works, right? If I didn't have this, what would it do? Nothing? Okay, what if I didn't have this? What will this do? Nothing. Okay, this does nothing. This does nothing. So adding these, make this work, right? What's the problem? ACNF. Yeah, okay. So there are some issues with this. There are some issues with this. So, for example, it's really easy to prove that these are commutative. So, for example, like here, right? We can just do a add no sign wrap com. And it's just like this, y equals x, right? It's just this. So this thing, you can just prove this. Oh, whoops. And then this is just like bit back. S add overflow com. That works, right? That's the proof. What was it missing? This is false implies that's false. That's just true. Why is it not simping more? And it's not working. Come on, simp harder. Oh, it's taking a while. Okay. Oh, and then you want It's taking a while. It's taking a long time. Okay. Thanks. So, alright. We can do this as well. Add no sign wrap. It's just like add com. Okay. So we can define associative for add, and then commutative for add, and commutative for add no sign wrap. But associative for no sign wrap, this is like not inequality. Like this isn't an equality. This is not an equality. This is like you would need to bring things down, but the ACNF tactic has no idea. It has no idea about associativity for when it's defined as a rewrite. It knows it has an idea of equality. It has an idea of equality, like everything works by inequality, but this is not equality. This is a rewrite. And it has no idea how to use that information. So, for example, this thing, right? You want to obviously canonicalize, I guess, how's it work? It canonicalizes the left-hand side, right? Yeah, it does, right? So I'll just change it to this side. Yeah, this doesn't, does it change this one? How does that work? This makes these all the same. Okay, so we basically want to go from here, which is really like this, right? Change this side. I think it goes the wrong way. But anyway, yeah. So we want to change this side. So no sign wrap to this, right? This can't really prove it. It doesn't do anything. So like going from this to this or the other way around, ACNF can't prove it because one, we don't have a type class for it. But even if we did, this doesn't work on rewrite. Like we'll just do an example of this, right? Add no sign wrap. This has no idea what this is. This is not, see how there's like this is an equality here, and then that's a rewrite like that. That's just not they're not the same type. They're not the same thing. So we can't do ACNF over rewrites because it's not a quality. It's just not a quality. Which is why we need which is why we really need like an optimizer like this. That's just the goal. That's just the goal. So what do? We just did this. Yeah, we didn't really do much, unfortunately. But like I'm gonna stop the stream. It's 2:20. Only been 2 hours. I'm gonna stop the stream. Hopefully, I can stream longer, much longer next time. Like much longer. Like this long even. But like until then, like I'm gonna work on getting this optimizer like working like perfectly, like working well, so you can actually prove stuff about it. Um, but yeah, yeah. Thanks everyone for coming. I appreciate it. Yeah. All right. Bye bye.